So we all know stream analytics can not only be done on Kafka. There is also other options to do so. The next speaker is a committer and PMC member of Apache Flink project, and he's been contributing to this project since the very early days. He's working at Data Artisans and currently working on a book on stream processing on Apache Flink. So while he's not doing that, he's here speaking for us with his topic today, why and how to leverage the power and simplicity of SQL on Apache Flink. Please welcome on stage Fabian Hüske.
Yeah, thanks. Thanks first of all for the organizers of this meetup to host me here. Thanks for all of you for showing up. Yeah, Max already introduced me. I'm a Flink PMC member. I'm also writing this book, so I guess he's seen this slide before. I'm also a co-founder of Data Artisans, and Data Artisans is a startup based here in Berlin. It was founded by the original creators of Apache Flink, and we're providing a solution called Data Artisans Platform, which integrates with Apache Flink and has a component called DA App Manager, which is meant to make the lifecycle management of streaming applications much easier. So this component basically helps you to fix bugs in your streaming applications, to migrate them from one cluster to another, to suspend and resume them. So all of these things, it's integrated with logging, metrics, and continuous integration and deployment. So all of that makes all these things around maintaining streaming applications in production very easy, and it's also built on Kubernetes. So what is Apache Flink? Who of you knows what Apache Flink is? All right, quite a few. I'm giving a quick intro nonetheless. So Apache Flink is all about stream processing. So it covers the whole spectrum of stream processing, starting at bounded streams, bounded historic streams, which you can also interpret as batch processing, going to classical stream processing like window operations, but also event-driven applications, so interacting with events as they arrive from a stream. It's a very scalable system. It processes data in memory. You can also go to disk if you have to do that. So we're also leveraging RocksDB for that. It supports event time processing, handles super large state, and guarantees exactly once state consistency. Flink is running in very, very large setups, so it's deployed in enterprises around the world. Uber uses it, Netflix uses it to process something like 3 trillion events every day. The applications that they do in hold 20 terabytes of state. It's used for financial applications in ING, for instance. Alibaba is a fairly big Flink user, so it's really running at very large scale. And it's not only used by those 4 companies here. It's used in very different industry, including Zalando here. So what abstractions does Flink offer? So we've heard Kafka offers also 3 programming abstractions like this pub/sub interface, Kafka Streams, and KSQL. For Flink, it looks pretty much the same. So we have the process function abstraction at the bottom, which gives you very much control about time and state, how to handle time, how to handle state, which are like the core ingredients for all stream processing applications. On top of that, there is the data stream API, which gives lots of built-in concepts like windowing operations, map functions, so all these things that you know from like batch processing like APIs. And finally, on top there is SQL and an API that we call Table API, which I'll show you in a second. So these are like Table API and SQL. Those are like the relation APIs of Apache Flink. There is ANSI SQL, which should look fairly similar to you. And there is also this Table API, which is a language integrated, so that's what LINK'S stands for, API. What this basically means is that you don't embed your query in a string and give it to your program, but instead you can use a fluent API to define all the operations that you want to do. So in this example here, we start with something table environment. We scan a table clicks. We group by user, and then we do a projection on that on user and count. So those two queries here are doing exactly the same. And the very important thing is that these APIs are unified APIs for batch and stream processing. And this means that a query specifies exactly the same result, regardless whether the input is batch data, like static data, or streaming data. So this is the very crucial part here. And how are these queries translated? So we're using Apache Calcite. We're building that on Apache Calcite, which is a query parser, query optimizer framework in Apache. And so the table API here on the top left, the SQL query on the top right, they both are translated into a common representation here, like a logical plan in Calcite. And then the Calcite optimizer is applied to that, optimizes this query, and depending on whether it's like static data, it goes into the FLINK'S batch API, the dataset API, or if it's streaming data, it goes into the data stream API. So which translation path is chosen depends on whether the data is bounded or not. So what if we have now bounded input for our query? So we're using this very simple query here. We have some file which has click data, and if we want to process that one, we just read the data, we somewhat give it into the query, and we get a result. The important here is that we basically read the input at once, and we also produce the data at once. So this is fairly standard. So basically, what pretty much all these SQL and Hadoop systems are doing. But what if SQL is a stream now? So in that case, we have some kind of schema, of course, and we have data appearing over time. So in this case, we have this one row with the user Mary. We put it into the query, and the query returns a single row with user Mary count 1. So if now the next row appears here for Bob, we add another row to the output. If another row for Mary appears, we have to update our result. So we have to say Mary has now a count of 2, and so it goes on. So the input is read continuously, the result is produced continuously, and the important thing is that the result is in both cases the same. So why is this batch processing, stream processing unification so important? So first of all, it makes the API very easy to use because it's the same SQL that you know from your database. So there is no custom stream SQL syntax here. There's also no custom stream SQL semantics here, which can be fairly hard to detect. It also makes the queries very, very portable, so you can run them on your historic batch data and later deploy them on your production live data. You can run it on historic data, live data. You can run it on bounded data. You can run it on unbounded data. So all of that makes this API very, very convenient to use. So what does it mean to run a SQL query on streams? So in fact, this is not really a very new thing to do. So who of you knows the concept of materialized views in database systems? All right, not that many. So who knows what regular views are? So a view is basically a query that you define and that you can then later reuse in other queries, right? A materialized view is very similar to that. So what it basically means is you, again, define your query as a query in SQL. And, but it's not a virtual thing. The database system will run the query and persist the data somewhere. And whenever you run a query that could potentially make use of this pre-computed data, the optimizer will kick in and replace some parts of your query with a scan of the materialized view. So this is a feature that is very, very useful for analytical queries. However, as soon as the base tables change of a materialized view, the database system also needs to update the materialized view that is stored on disk or in memory. And this process is like an incremental update of the result. And this is very similar to running a SQL query on streams. So this is, as I said, not a very new thing. So you basically can consider the view definition as a continuous query, the stream of data as the changes that are applied on the base tables of the view definition, and later the materialized view itself is the result of the query. So database systems are doing that for decades. In Flink, we call this concept of changing tables dynamic tables. And when you have such a dynamic table that basically changes over time, and you reply a query on that, the result again will be a dynamic table, right? Because as soon as the input table change, the query will adjust the output table. So what is like this is like the core principle of how Flink treats this batch streaming unification. It basically means evaluating a regular SQL query incrementally as the input changes. So what is the feature set covered in Flink 1.5 that was released like a month ago? So we have like all the regular select from where queries. You can do group by having queries without windows, also without tumble, hop, and session windows. There are a couple of joins supported, including stream joins. Also, lots of UDFs are supported that allow you to get your custom code into a SQL query. And there is also a bunch of some features which are only supported in either batch or streaming yet, but we're working on closing the gap between these APIs. So what can you actually build with that? So a very common use case is like data pipelines, transforming, aggregating, moving events in real time, low latency ETL, ingesting a stream, and then writing the data into a file system or into a database system, maintaining then within the database system something like a materialized view, which is computed by the stream processor. So the database will then hold always the most recent result of your query as it was ingested from the stream. And then you can, for instance, also connect Tableau to that database and then always run queries on the most recent table that is maintained by a streaming query. You can run batch stream analytics things first on batch data, later on streaming data, or the other way around, and also use it to power like live dashboards, for instance. So here I'm showing I'm not showing a nice live demo. Instead, I'm walking you through a few example queries. We're using this, I guess, fairly well-known taxi ride data set here, which is based on taxi rides from New York City. We have the taxi rides. We made the data set a little bit simpler. So it basically has a ride ID for each taxi ride. It has a flag, whether this is a starting event or a stop event. So start event here means when the driver picks up the passengers, and stop event means when he drops them off. We have the longitude and latitude of these events, and also timestamp when each of these events happened. And with that, you can build queries that, for instance, compute every 5 minutes for every location the number of departing and arriving taxis of the last 15 minutes. So this is a typical streaming analytics query. Here in the query, I highlighted the parts that correspond to each of the different aspects of the query. So we obviously want to count something per location. So this is like an aggregation query where we need to apply some kind of grouping. We want to group on departing and arriving taxis. That's why we group on the start flag, which is a Boolean flag. We want to group every 5 minutes for the last 15 minutes. This is something that is known as hopping window. You see the hop window clause in the bottom where it says row time, which is the time attribute of each row. We say interval 5 minutes, which means every 5 minutes we want to read the data, or we want to group the data of the last 15 minutes. And then in the end, we simply say the aggregation is then a count star. So this is a very, very common and simple aggregation query. Something that's a little bit more advanced is a query where we actually want to join two data sets, two streaming data sets. Here we want to basically connect the start events and the end events, and want to compute the average write duration per pickup location. So what we do here is we first have two subqueries that where we filter once on the start event is true, and the other one is where the start event is false. So we have this one table. We separate it into the table with all start events and the other one with all stop events. We compute this to cell ID. This is a user-defined function which takes the longitude and the latitude and then discretizes them. So like joining on longitude and latitude values doesn't make a lot of sense. So we basically discretize that into cells of 100 by 100 meters. And later on, we join those two tables. And the interesting join condition here is the one with the row time, where we say the timestamp of the end row should be between the start row time and the start row time plus 1 hour. So we basically here assume that each taxi ride only takes 1 hour. And this join condition ensures that we match the starting events with the end events. So these are like the things, the type of queries that you can do with Flink SQL here. Yeah, and one application you can do is basically you have the data coming in from Kafka, for instance. You then run a Flink SQL query on top of that, write the results to Elasticsearch, and later use, for instance, Kibana to display the results here. Something that is coming up in the next version of Flink, which is something I'm very excited about, is unifying Flink's CEP library, complex event processing with SQL. In the most recent SQL standard, SQL 2016, there was a feature introduced called match recognize, which can be applied here in the from clause. And this basically lets you define patterns on tables. And this is obviously very interesting for stream processing, because with that you can basically analyze your stream, identify interesting patterns, and later do analytics on top of it. Or you first do analytics or process the data in any way with SQL, and then you try to detect patterns on it. So that's a very powerful combination of features: SQL for analytics and CEP for pattern detection. All right, and just to summarize, the unification of batch and stream processing is fairly important in our opinion. Flink SQL solves many of the streaming and batch processing use cases. It runs in production at Alibaba, Uber, and others. So it's actually also not only Flink, but also Flink SQL is used at very large scale already. And the community, as usual, it's an open source project. It's working on improving all the user interfaces. And if you're interested in that, get involved, start discussing and contributing. Something that I like to mention as well is we're going to have the Flink Forward conference here in Berlin in September. It's the 5th edition, so we are here in Kulturbrauerei for the 5th time. Early bird prices are still available until early July. So if you're interested in stream processing, you're here in Berlin or close to Berlin, you should definitely check out the schedule, which will be announced in the next days. And with that, I'd like to thank you, and I'm open for your questions.
Thank you, Fabian. Are there any questions in the audience?
Over here.
I take this one first, and then it comes back to you.
So yeah, maybe a very general question, what I like it. So looks very similar to Kafka SQL, and what is your advice when to choose what?
Is that a trick question or?
No.
I mean, it's going to be
here.
Right?
I like also on GitHub projects when I discover new stuff, I always put an issue and say, how do you compare to X, Y, Z? And I like Flink very much. I used it only a few times, but I also like Kafka. And yeah, I just would like to hear your internal opinion on when does it make sense to use what, because I think it's very pragmatic, especially for people entering the topic.
Yeah, that's true. So, I mean, Kafka Streams is we've seen it's super easy to use if your data is already in Kafka, right? Flink is following a more, I'd say, more general approach. So we're also integrating with other data sources, for instance, Kinesis. You can also read your data directly from HDFS. When you want to use this feature of batch streaming unification, if that is important to you, obviously you should consider using Flink for that. Yeah, so I think like this batch streaming unification is like is one of the big differentiating features.
Okay, thanks.
Well, I basically had the same question, so next one.
Any other question? No? Then I want to thank Fabian once more. We are now